Have you ever just looked up at a giant bridge or a massive skyscraper and thought to yourself, how did they know that would work? How can they possibly be sure it's not all going to come crashing down? Well, today, we're going to pull back the curtain on the incredible, invisible engineering that keeps our world safe. It's a technique called finite element analysis.
I mean, think about it for a second. It's a real head-scratcher. You can't just build a billion-dollar bridge and then, load it up with trucks until it snaps. And you definitely can't test every little part of a machine until it breaks. So how in the world do you find the breaking point of something that's just too big, too expensive, or even too complex to test for real?
Well, it turns out the answer lies in this brilliant engineering trick, and its strategy is super simple: divide and conquer. This is the whole idea behind finite element analysis, or FEA for short. It's the magic that lets engineers test the impossible, and it all happens inside a computer.
Okay, so the core idea here is actually super elegant. Instead of trying to solve one gigantic, impossibly complex physics problem all at once, engineers do something called discretization. Honestly, the best way to think about it is like building a really complicated shape out of Legos. They break the object down into thousands, sometimes millions, of tiny simple pieces called finite elements. Each little piece has a math problem attached that's easy for a computer to solve.
So here's how it all comes together. First, an engineer builds a 3D model of the object on a computer. Then, the software slices that model up into a mesh. That's our collection of finite elements. Next, they apply virtual forces. We're talking about the weight of cars on that bridge, or maybe the intense heat inside an engine. Then the computer does the heavy lifting, calculating the effect on every single element. And finally, it stitches all those millions of tiny answers together to give one complete picture, showing exactly how the whole thing is going to behave under pressure. It's genius.
So, where is this amazing technique actually used? The answer, and this is not an exaggeration, is pretty much everywhere. We're talking from the absolute biggest structures we build, down to the tiniest little parts inside of them. The sheer range of this stuff is just staggering. Engineers use FEA to figure out the immense stresses on a massive bridge deck, right? But then they use the exact same principles to study the wear and tear on a tiny little ball bearing. It doesn't matter if it's a giant crane hook or a microscopic component, that divide and conquer method just works.
And this is where it gets really mind-blowing. The versatility is just incredible. You've got biomechanical engineers using FEA to model the human spine, right from a CT scan, to understand back problems. And at the very same time, civil engineers are using it to model huge steel joints in buildings. It's the same powerful tool, just being used to understand both our own bodies and our biggest structures. Wild!
And FEA isn't just about asking, hey, is this going to break? Oh no, it's way more sophisticated. It's like giving an object a complete physical checkup. Engineers can see stress points light up, they can predict how a material will bend and return to shape, they can map out how heat flows through it, and even simulate how fatigue builds up over millions of cycles to predict exactly how long a part will last. They can see the future of a design before it even exists.
So, what does this actually look like for an engineer on a Tuesday morning? Well, they're not just sketching on a whiteboard. They are using some seriously powerful software. It's basically a digital proving ground for all their ideas.
These right here are the digital workhorses of modern engineering. You've got these huge software packages like ANSYS, Abacus, and SOLIDWORKS Simulation. These are the virtual labs where engineers build their models, create that fine mesh we talked about, and then run these massive calculations to simulate real-world physics. This is where designs get tested, tweaked, and ultimately perfected.
Okay, this all sounds incredibly powerful. I get it. But why does it really matter to us? What's the actual real-world impact of being able to see these invisible stresses hiding inside a piece of steel?
The result is, frankly, profound. It leads directly to a world that is safer, more efficient, and way more innovative. Instead of spending a fortune to build one physical prototype, engineers can now test thousands, literally thousands, of different designs virtually. They can find every little weakness, optimize a part for both strength and weight, and just push the boundaries of what's possible, all before a single piece of metal ever gets cut.
And the benefits are things you can actually touch and feel. Because of FEA, we can accurately predict the lifespan of the bearings in a giant wind turbine. We can optimize a circuit board so it doesn't overheat. We can be absolutely certain that a new skyscraper design can handle the most extreme weather conditions. It creates this amazing feedback loop. where the virtual world and the real world make each other better, safer, and more reliable.
So this all brings us to a really fascinating final thought. We now have this virtual proving ground where we can test nearly anything we can possibly imagine, from revolutionary new materials for spacecraft to the complex biological systems working inside our own bodies. The question really isn't, can we build it safely anymore? The real question is, what impossible challenge are we going to solve next?